Hello, welcome to the lecture on BMS Safety, and thank you for joining me in the transition to sustainable energy. This lecture on safety is split into 4 video clips. The lecture begins with general safety concepts applicable to any design requiring a similar level of safety as cars, though my examples will all feature battery management. If you're already familiar with fault trees and DFMEA, you can skip videos 2 and 3. The 4th video is mostly focused on BMS safety. Now, in the first section, we'll discuss categories of faults, some organization being essential to applying the analysis tools effectively. Faults and system responses to faults can be categorized into different levels. Some systems have no fault tolerance. For example, a plastic spoon. If it breaks, that's it. If it breaks, it no longer works. And that's totally sensible for an inexpensive thing whose failure has minimal safety consequences. Many large battery systems have single-point fault detection. This means that if any single-point fault occurs, the system can detect it, but not necessarily continue operation. For example, if a contactor fuse is closed and is no longer able to open, a BMS should detect the fault. However, there probably is no redundant contactor, so with this fault, we should stop operating the product until it is repaired. Let's consider a system with single-point fault tolerance. Brakes. In many cars, the foot brake and hand brake are independent enough that if the foot brake fails to work, you can apply the hand brake. Motorcycles and bicycles have front brakes and rear brakes, independently operated. If one fails, the other can still stop the vehicle. Implementing single-point fault detection versus tolerance is pretty different. For single-point fault detection, we need something to do the detecting, some sort of diagnostic sensor. And importantly, the diagnostic sensor needs to be diagnosable too. We want to catch any single-point failures, whether in the component itself or in the diagnostic subsystem. For single-point tolerance, solutions vary. If the component is an actuator, the system needs something else that can fulfill the actuator's purpose when that actuator is broken. We need a redundant actuator. For example, if the foot brake fails, the hand brake fulfills that redundancy. If the component is a sensor, a single redundant sensor isn't enough. Imagine that one sensor reports 3 volts and a second sensor reports 5 volts. The discrepancy indicates one of them is broken, but from just that, we cannot know which one. And that means we cannot keep operating. In this case, we don't know whether our cell is at 3 volts and ready to charge more, or at 5 volts and dangerously overvoltaged. We need 3 redundant sensors to allow continued operation if one fails. For example, if 2 sensors report 4 volts and one reports 5 volts, which do you think is faulty? With the assumption of a single fault, we can say that the one sensor that doesn't match is faulty and rely on the others. Another viable option is 2 sensors with diagnostics. Say the 2 sensors provide conflicting readings. We initiate our diagnostic routine, and the diagnostics let us know which reading to trust. Let's apply that to an exercise. List some battery products that might fall into each of these categories. Here are some that I thought of. Products with a small battery and where loss of operation is a minor inconvenience usually don't warrant fault mitigation. Products where a battery fault could cause a safety issue, such as a significant fire, call for single-point fault detection. In these systems, we want to ensure that if anything goes wrong, we stop and transition to the safest available state. Applications where loss of operation is a critical problem call for fault tolerance. These are systems in which it's really bad to stop. For example, loss of function in a satellite is very expensive, and loss of function in a self-driving car could cause a life-threatening accident. Even if a fault occurs, we'd like that satellite to keep operating and that self-driving car to pull over in a controlled manner. And now, a few words on types of faults with examples. This builds intuition that will help understand what the analysis tools that we'll discuss do and don't capture. Let's list a few examples of faults before defining fault categories. A cell internal short is a fault in a core component. If the battery is 1P, meaning only one cell in parallel, a faulty cell disables the whole battery. The system goes down. A cell short can cause exothermic behavior and smoke and fire, unsafe in itself. What if a contactor fails and refuses to close? A contactor is another core component, and the system won't work if we cannot connect the battery. However, this is not unsafe in itself. An open switch alone won't cause a fire or an electric shock or further damage. What if the diagnostics fail to run? Perhaps we have a firmware bug, or perhaps some circuit responsible for implementing a diagnostic is damaged. This does not stop operation and is not unsafe in itself, but it's not inconsequential. Our system, intended to be single-point fault tolerant, is running blind and possibly no longer able to respond gracefully to some subset of subsequent faults. What if a current sense wire breaks? A broken sense wire does not in itself stop operation, and again is not unsafe in itself. An open wire won't cause fire or shock anyone, but it undermines important controls, and we might see collateral faults in short order. We can group faults by what breaks. Is it a core component that in itself stops the system? Or is it some sensor or diagnostic whose failure alone does not interrupt operation? And we can consider consequences, whether the fault is unsafe in itself, or whether it might start a chain of trouble, for example, providing incorrect information to some controller, or whether the fault has no impact because our system has enough redundancy to continue operating in the presence of this fault. Some faults stop operation. Some faults don't. Let's consider the impacts of both scenarios. The system stopping when some core component fails can be good. It prevents further operation with a fault. For example, if the communications wires to our contactor fail and we cannot shut the contactor, that's a good way to fail. We won't activate a broken system. But losing function can also be bad. A controlled shutdown may be safer than an abrupt shutdown. For example, if something goes wrong in its battery and a car immediately loses power, it will stop wherever it happens to be, whether that location is a good place to stop or not. Continued operation after a fault can be good if we, the engineers, design the system well. If the system detects the fault, the engineer can design a graceful shutdown. For example, if we lose a cell voltage sense wire, perhaps we allow continued operation to allow the driver to decide when it's safe to pull over, and delay disconnecting the battery until the car is safely parked. Operation after a fault can be bad if the fault is undetected and the faulted component is necessary for safe operation. For example, an undetected temperature sensor failure may allow operation at a temperature that damages the cells. Oftentimes, systems consist of core components whose failures stop operation, plus sensors or diagnostics, without which the system continues to function, though sometimes poorly. Faults also differ in how immediately they cause trouble and how quickly the system ought to respond to them. Some faults are in themselves instantly dangerous, such as a cell going exothermic. Some faults warrant an immediate stop in operation. For example, if the motor control current sensor fails, the motor controller may lack information necessary for basic operation, and the system should stop operation right away. Other faults warrant stopping operation eventually, but not necessarily immediately. For example, a fault in our temperature sensor precludes long-term operation, but we certainly can allow a few minutes for the driver to pull over, or perhaps even some hours with reduced power. And some faults are nearly inconsequential. For example, if we have more sensors than the necessary minimum, we can tolerate the loss of a sensor with no loss of system function. What exactly do immediately and eventually mean? Do we mean 100 microseconds, 1 millisecond, 1 second, 1 day? The functional safety approach defines a fault-tolerant time interval, or FTTI, to every fault to capture this idea. An FTTI defines a concrete number. A current sensor fault may have an FTTI of hundreds of microseconds or a couple milliseconds, depending on the corner frequency of the control system using the current measurement. A temperature sensor fault may have an FTTI of several minutes. No metric is perfect, and some faults are tricky to describe with an FTTI. For example, if the charger experiences a fault while driving, perhaps the system cannot charge, but it may well be able to continue operating and discharging the battery until the battery is empty, which could be 10 minutes or 10 months. Faults also differ in their severity, or how much they affect the end customer. Most severe are faults affecting safety, followed by faults that reduce performance. Faults that affect most customers are more severe than faults that affect fewer customers. And faults that have no visible effect on operation are assigned lowest severity. DFMEA assigns numerical values to severities, which we'll discuss later. Faults differ in their likelihood of occurrence. This chart is for failures in an automotive clutch, but you could make a Pareto diagram for any system. In our battery world, we might be evaluating connector failures versus erroneously flipped digital bits. Perspective on the rate of occurrence can help us prioritize design effort towards detecting and mitigating the more likely failures. Faults differ in how easy they are to detect. A cell overvoltage is highly detectable. The first thing we implement in a BMS is cell voltage measurement. So for sure, we're measuring cell voltage and doing so fairly frequently. One of several parallel cells being disconnected is harder to detect. A typical BMS doesn't have a specific sensor dedicated to this failure, but we could implement an algorithm to estimate the capacity of each group of parallel cells, which would show us that a P group has changed from 30p to 29p. Some failures are undetectable. For example, if the value of a balancing resistor drifts due to aging, a typical BMS has no mechanism to detect this. And zero detectability is okay for some failures, perhaps those with low severity and infrequent occurrence. To summarize, it's important to consider the type of failure when deciding about mitigations. We should be mindful about what broke, the consequences of the failure, including both the severity and the time scale, the probability of occurrence, and our system's means for detecting the failure. This is the end of video clip 1 in the lecture on BMS safety. Please continue the lecture with video 2.